Hello, my name is Matthew Harrison. I'm a Professor of Sustainable Agriculture based at the University of Tasmania in Launceston. In a previous video, I looked at what crop models are, how they've been historically developed, how you typically apply them, and how we calibrate crop models. And that's the process of tuning model parameters such that the model outputs best match observations. In this video, I'll look at using those calibrated model files and comparing the simulations against independent data sets. And that's the process known as validation. I'll look at validation statistics and what to do when validation fails. So model validation is known by various names, sometimes known as evaluation, sometimes known as verification. Some people actually treat verification as a slightly different process. The important part about validation is that it needs to be used on independent data sets. So the data sets that you use to validate your model cannot be the same ones that you use to calibrate the model. For example, you might use soil carbon data sets sourced from the peer-reviewed literature to calibrate your model. You then are comfortable with the calibrated model. You then need an independent set of data, for example, an independent experiment or a new site. You run your calibrated model and you test the quality of your calibration, which is the process known as validation. You can't use the same data as you use for calibration. You need to conduct validation using high quality data. So it's worth investing the time to search the peer-reviewed literature to find that calibration and validation data. Yes, it is time consuming, but it's well worth the effort. You do have to set up for each peer-reviewed experiment that you want to simulate. You do have to set up the management conditions in your model, sowing time, fertilizer amount, crop type, to simulate it in order to validate it, and it is time consuming, but high quality validations are well worth the time investment. In calibration, you should be placing more emphasis on ensuring the accuracy of your model inputs, particularly the uncertainties. You might have a measured soil data set, but you might not actually know with certainty, or you might not know the variability in soil lower limit, for example. That does give you some scope to modify the lower limit to change what might be soil moisture stress, and that will change the trajectory of simulated dry matter. So you're better off changing your model inputs, particularly those that are uncertain, rather than excessively calibrating, particularly parameters that are hardwired or default plant parameters that you shouldn't be changing. There's a number of different validation statistics that you can use. You can use intentional separation, where you separate one treatment from a data set and use that as for validation, or you could use holdout validation, which is typically a process done with spatial data where we withhold a large proportion of the data, for example 70 to 80%, and on the remaining data we do the validation, and that can be iterative. A subset to that is k-fold cross-validation. So the algorithm typically automatically does this. It divides the data set into k subsets. It trains the model on k-1 subsets and tests the model on the remaining set. And then it forms a validation result and validation statistics, which I'll talk about later. And then it averages the result across the k-folds. The important point about k-fold validation is that for the set that is reserved, it's not actually used in validation. So validation, again, is conducted independently of calibration. It's doing it in an automated way. Then you have stratified sampling. And so that's where you have imbalanced data sets. And it's particularly useful for when you're calibrating soil types, which are typically divided into irregular strata, which might be based on a particular soil type or a land management or agroecological zone or a combination thereof. There's many different model validation statistics that people can use. One of them, which is a very common one in the peer-reviewed literature, for example, is the root mean square error or mean absolute error. Another one, which is a subset of that, is the root mean square error divided by the mean of observed data. So that's normalized root mean square error. I find that more useful than root mean square error per se. There is the typical R squared coefficient of determination, which basically explains the variance in observed data explained by the model. You can then plot your observed data against your predicted data, and ideally that would all fall against a one-to-one line. There is percent bias, which measures the average tendency of simulated data to be smaller or larger than observations. You have model efficiency, which compares the variance of your predicted errors against the variance of your observed data, and obviously you want the variance of your predictions to be lower than the observations. Index of agreement's an interesting one because it, in contrast to the coefficient of determination, index of agreement, or D, measures both additive and proportional difference between your observations and your simulations. So in the next few slides, I'll go through the calculation for each of these model evaluation statistics and what you should be really looking for. So the root mean square error, which is by far, well, not by far, but one of the most common, it measures the average error between predicted and observed data. You typically sum up the difference between your predictions, P, and your observations, O. You square them, and then you take the average, and then you take the square root of that. So a value of 0 indicates perfect agreement. In practice, it's quite rare to get a value of 0. As I mentioned before, I think the normalized root mean square error is better, which is where you calculate the RMSE and then divide it by the average observed value, because that gives you a normalized root mean square error of 0.1 is appropriate. A value of 0.3, which indicates 30% error, is getting quite high. The problem with RMSE is it's very sensitive to outliers, and that's because of this squared term here. And so if you have one or two outliers in your predictions, the RMSE will go up considerably. An improvement, I would say, on RMSE is mean absolute error, calculated in a very similar way, except it's taking the absolute difference between each observation, OI, and each prediction. And then you sum them up, you divide by the total number of points, and it gives you the mean, basically the mean absolute error, or the mean absolute difference between the observations and the predictions. Because it's an absolute, it can't be negative, so it ranges from 0 to infinity, with 0 being ideal. It's got much lower sensitivity because of this to outliers, because of this absolute term, versus root mean square error because of the squared term. Then you have percentage bias. That's the average tendency of the predicted values to be larger or smaller than your observed data. Similar sort of calculation, and most of these evaluation statistics are calculated in a similar way, but they tell you something different. After I've explained each of these, the calculation for them, I'll tell you what they actually can be interpreted as, which I think is quite important. Percentage bias quantifies the percentage deviation, which actually allows comparison across scales. Similar to the mean absolute error, a value of 0 is ideal. Value less than 10 is very, very good. Hard to get though. Positive indicates underestimation and negative indicates overestimation. It's a standardized way for comparing across metrics or variables or data sets. You have then the Nash-Sutcliffe efficiency, or NSE. It compares the residual variance of a model against the residual variance of the observed data. And again, calculated in a similar way, so it's 1 minus the sum of the squared differences between the observations and the predictions, divided by the sum of each observation minus the mean of the observed value. So if you take note of that denominator there, what it's actually telling you is it's comparing your predicted values, P, against the mean of the observed value. Now, if you get a value of 0 for NSE, where this term actually equates to 1, that indicates that you've got a naive model. So your model is predicting no better than the mean of the observed data. Ideally, your NSE is as close as possible to 1. A value of less than 0 indicates that your model is actually worse than the mean of the observed data. Because errors are squared, again, similar to RMSE, the Nash-Sutcliffe efficiency is highly sensitive to outliers, so a better approach might be to replace these squares with absolute values. Then you have the index of agreement, or D, which measures both the additive and the proportional difference between observations and simulations. So on the numerator here, we have, similar to many of the previous evaluation statistics, we have the sum of the observations minus predicted values squared. And the denominator is a little bit different in this case. So we're doing the absolute difference between each predicted value and the mean observed value, plus the observed value minus the mean of the observed value, all squared. It ranges between 0 and 1. It's sensitive to extreme values because of that squared term. And unlike the correlation coefficient, it's not based solely on linear regression, but it also considers the magnitude of the differences between predictions and observations. Then you have model prediction error, or MPE. Model prediction errors can occur due to many reasons: structural or parameter or input or user or random errors. An appropriate model validation is one where, for example, 90% of your prediction intervals from your model contain 90% of the observed data. Note that that's an arbitrary threshold though. For non-Bayesian models, and I talked about what Bayesian models are in my first video in model calibration, model prediction errors can be computed as, and they can be computed in many different ways, as the standard deviation of the model residuals, which is the difference between the predicted values and the observed values, and you multiply that by the 90% z-score, which is 1.645. So how that's computed in practice is you difference each of the predicted values and the observed values, and you subtract the mean residual value. The top line is squared, and then you divide that by k minus 1 and take the square root of the whole thing. And then the 90% prediction interval is calculated for each prediction. So you, for example, you do the prediction minus 1.64 times this term, and then the prediction plus 1.64 times that term. And the 1.64 is the 90% z-score of a standard normal distribution. How would that work in practice? You can actually do it for each replicate observation, provided you have replicates. In many peer-reviewed publications, they don't provide them. So if you had to calculate the differences between the predicted and observed, so on the bottom here in this graphical example, you have your predictions, it might be soil carbon, then you have your observations. You then compute uncertainty of your model results, which are considered as a group, so you're getting the variance here, and then you do the calculation that I described on the previous slide, take the square root of that, and you get the effectively the standard error of the model residuals. It's okay to take account of other project-wide factors when you compute uncertainty. This is really just an example. And then you generate your 90% prediction intervals for each modeled effect. Again, this is on the withheld data, so we're talking about validation here. And you would generate something like this, where the point is actually where the big dots are the observation and the point is the model error. In this case, because we've got the same plus 1.64 and minus 1.64, we've got the same width of the error bar either side. And it's okay for up to 10% of your observations to be outside the model prediction. And again, the 90% prediction error is an arbitrary threshold. If you're dealing something like a carbon program, the more observations you have outside the uncertainty, the prediction error, the greater your uncertainty deduction. So it's in your best interest to have as many observations within the model prediction error as possible. It's also important to note that the observed values probably will have some uncertainty in themselves. How does it actually look in practice? People typically use a Gaussian distribution or a standard normal distribution. Higher z-scores indicate a lower chance of occurring and therefore greater significance. So on the top row here, I've shown the p-values, so 0.1, 0.05, 0.01. Corresponding to those p-values, I've got the z-score. So the corresponding to the 90% z-score is 1.65. That's a 90% prediction interval. If you wanted the 95% prediction interval, that would be a z-score of 1.96. And if you wanted the 99% prediction interval, which means that your prediction interval should cover 99% of observations, you would use a z-score of 2.58. And then you have confidence intervals. So these are probably more common in statistics. So it's the probability that the observed value of X lies within one standard deviation to the mean, and then you've got probability of X lying within two standard deviations is 95%, and and the probability that a given value lies within 3 standard deviations of the mean is a little bit over 99%. And again, that's similar to the standard normal distribution that I showed on the previous slide. It's important to note that a prediction interval is not the same as a confidence interval. So what I've shown here is prediction interval against the standard z-score. Note that the y-axis there is in a log scale. The z-score could be interpreted as standard deviation. So for a z-score of 1, you have a 68% prediction interval. In contrast, and this is where I was coming to from the previous slides, if you have a 90% prediction interval, that corresponds to a standard z-score of 1.645. And so it's important not to confuse confidence intervals with. So a bootstrap prediction interval is a little bit different to the prediction intervals that I've previously spoken about, because what it actually does is it subsamples the population, and then it repeatedly samples those subsamples to generate a distribution associated with those samples. It then fits a model to each of those subsamples, so it doesn't assume a standard normal distribution. So for example, if you had a 90% confidence interval, what bootstrapping would do is it would generate a distribution for each of the 5th and the 95th percentiles of your prediction interval. So an original data set is resampled a number of times, it might be B times, and then you fit a model on each bootstrap sample. Could be a linear regression, could be something else. And then for each specific input value, a prediction is generated using each of the B models. So to give you a practical example, you might have a population, for example, human heights, which you'll never know the full distribution of human heights simply because you cannot measure the height of any particular person. And if you did, by the time you finish measuring them, the height of the first people you measured probably would be different. So we take a subsample and we can determine the number of heights of those. But what bootstrapping does is it resamples that subsample. So every time it takes a single value out, it takes the value and then it pops it back in again. So the red values are those that have been taken and put back in again and resampled again. The brown values or the orange values are those values that are only drawn once. And then with all of those repeated resamples with bootstrapping, we then compute the statistic X, and then you come up with a frequency. Here it's a little bit like a normal distribution, but it could be anything. And you come up with a frequency distribution for that particular statistic X. So how do we actually interpret and how do we actually visualize those model validation statistics? So in the next few slides, I've just shown a few illustrations. Note that the data is synthetic, it's manufactured. On the x-axis, I've shown the observed value. Here I've shown observed soil organic carbon stocks. And on the y-axis, I've shown simulated soil organic carbon stocks. In this case, your simulated value is not changing for a whole bunch of observed values. So your simulated value is probably 55, and it doesn't matter whether the observed value is 10 or 100, your simulated value is getting exactly the same. In that case, you would have a Nash-Sutcliffe efficiency of 0. You then might have a case where the majority of your simulated values are similar to the observed values, and that's what we want. We want them to fall along this one-to-one line, but you have a few outliers. Not many, but a few. In that case, you'd have a high root mean square error, and you'd have a moderate R-squared value. In the case where you have high scatter, you would have a modest to low R-squared value, and you'd have a high root mean square error. You could have the case where there's a good correlation between the simulated and the observed values. So you'd have a high R-squared value, but you've actually got a high bias. And then a good model would be one in which the simulated values approximately fall along the one-to-one line, which is this solid line here. So you'd have a low root mean square error, you'd have a high R-squared, and you'd have a low bias. So putting it all together, a perfect fit or an ideal model would be one in which you have a high R-squared, you have a Nash-Sutcliffe efficiency of about 1, a percentage bias of 0, and a low root mean square error. If you've got that case where you have a constant bias, you could have a higher root mean square error, R-squared, and percentage bias, but your Nash-Sutcliffe efficiency would be moderate. This is why it's important to compute multiple validation statistics, because they all tell you something different. If you had the case where you have high scatter, you might have low R squared, low NSE, and a p-bias of about 0, but you might have a high root mean square error. If you have the case where you have a few outliers, which we showed before, your RMSE and your R squared could be high, and your NSE may be moderate, and your p-bias might be close to 0. If you've got the case where the mean of your observations is similar to the mean of your predictions, where you've got a model with really no skill, so your RMSE would be moderate and all of your other indicators close to 0. If you have a model that, for example, produces reduced predictions as your observations are increasing, well, then you've got a very poor model. Your RMSE could still be high, and your p-bias could be high. Your root mean square error would tend to be low, and your NSE would be negative. So thinking about these validation statistics, what are they actually showing us? Root mean square error is really showing us the accuracy of your model, or more specifically, normalized root mean square error. R squared is showing the percentage of variance accounted for by the model, and you're wanting that to be higher rather than lower. NSE is showing, or your Nash-Sutcliffe efficiency, is showing your predictive skill versus the baseline, and you're really wanting that to be close to 1. And your p-bias is showing, your percentage bias is showing your systematic error. And the most important thing is your interpretation. Really, we're just putting statistics on, numerical statistics on this to facilitate interpretation. At the end of the day, it's really your interpretation of your model versus predicted. Time series are particularly important in that respect, because most crop models are simulating output variables over time. What do you do when model validation fails? Well, it might not be the model that's the problem, it might be the measured data. So which one is the problem? Investigate your measured data quality and extent. Look at your climate data. Look at your measured data. Have you used bias data? Have you used enough treatments? Have you used enough experiments? Look for outliers. Are they legitimate? Are they realistic? Or could they be artifacts? Think about whether your model contains the fundamental mechanisms that you're actually trying to simulate. If you're trying to simulate extreme heat stress on, for example, wheat yield, well, you might want to look at, do you get senescence? Do you get crop death when extreme heat is above 35 degrees Celsius, for example? A lot of these models were developed historically not for average conditions, not containing appropriate formula for extreme. So look closely at whether your model contains the functionality for the process or the objective of your exercise. Look at the sensibility of the outputs. Look at the magnitude of the data. Look at the time course. Compare it with peer-reviewed literature. If you're not sure what soil carbon stocks should be, look at empirical values measured in the literature. For the top 30 centimetres, they should be between, say, 20 tonnes of carbon per hectare, maybe up to 70 or 80 tonnes of carbon per hectare if you're lucky. If your model simulations are outside that range, you might want to question whether your calculations or your units are correct. If the calibration's good but your validation's poor, that might be overfitted, so it's highly specific in one case, highly accurate in one case, but poor when you validate it in other cases. Really, you want generalized model performance, so that means you've got a good fit for multiple treatments and multiple sites. Not perfect, but good fit. So when you use it for new contexts, new scenarios, that your validation is going to be appropriate. You don't want it to be very accurate for one site or treatment, and then when you use it in a new context, it completely breaks down. That indicates overfitting. And I mean, all of these equations R has a number of standard algorithms for, and you can, once you've coded them up into R, you simply pop your observations and your simulated data in there, and it'll spit out each of these evaluation statistics automatically. That's all I've got to say for today, and thanks very much for listening.